Well, good morning, everybody, and welcome to Ellensburg, Washington, USA. The local time is 11:48 a.m. Pacific time, and in about 12 minutes from now, we will begin a lecture, and you can see the title slide on your screen right now, I hope. Head for the Hills, Potential Tsunami Sources in the Salish Sea, and our speaker today is Lucinda J. Leonard from the University of Victoria in British Columbia, Canada. We are live right now, and I'm looking at the live chat and hoping to see some 5x5s. And once I see that, I'll get on camera and say hi to a few of you. There's a bit of a delay in the comments, which is also always slightly unnerving. But we will hope for the best here in just a moment or two. I see Dublin, Ohio. Are we 5x5? 5x4, 5x5. That's enough 5x5s for me to make me feel good. Thank you for that. Wonderful. So hi, everybody, and welcome back. I'm so glad that you're joining us live or in recorded form for this last Friday talk of the school year. Final exam week is next week. People are on fumes, limping into the finish here. Many are still in volcanology with Hannah Shamloo, and they're running long, so that we have mostly an empty room here, but we have plenty of townies joining us today, and a few professors and some others coming in, so it's a good scene. So I'm glad that we're 5x5. Let me say hi. Where are you viewing from today? South Africa, Boulder Creek, California, Houston, Texas, Indiana, Charlotte, North Carolina, Tacoma, Lithia Springs, Georgia, Norway, hello, Stratford-upon-Avon, England, hello John, Albany, Oregon, Marysville, Washington. Let's keep going with the reports here of where you are viewing from. We'll do a few extra. It's mostly an empty room. I don't think I want to show it to you. It's mostly an empty room, but it's quite lively, I must say, and people are starting to filter in. Kingsgate, Washington, Miamisburg, Ohio, Salem, Oregon, Seattle, Washington, Orangevale, California, Frisco, Texas, France, Fennoscandian Shield, Garrett, the Dutch Night Owl from the Netherlands, and Norley, if you happen to be watching, get well soon. Tri-Cities, Washington, Horseheaven Hills, Washington, Everett, Washington, Centralia, Washington, heard of it, Spokane, Washington, there's Adele in Disco Park, see you tomorrow, Adele, Two Rivers, Oregon, Hillsboro, and so on. Good. So we have 156 live viewers, and I suppose that number will continue to increase. This is a sexy topic. Head for the Hills, the potential for locally generated tsunami in the Salish Sea. So before I turn the camera around and give you a sense of the room, people are enjoying the Vinman's products delivered personally by owner Jeff, and I'm in a nostalgic mood. Hannah Shamloo and I started this series 2 years ago, and it was mostly an empty room, and there was not a whole lot of energy in the room. It was just kind of a dead scene. And so Hannah and I thought very carefully about how to create a place that was full of life, full of welcoming people, and got all of not only our department together, faculty, staff, grad students, and undergrads, but also people from town. And that is happening now. I'm so pleased to report it's happening, and it continues to happen. So Hannah and I will continue next year with our planning, and we'll continue to make some tweaks, but for the most part, it is a success, and it's just one of many things that Hannah Shamloo in particular has been doing in the last 2 years that have just dramatically improved our culture here in the department. It wasn't a terrible place, it was a good place, but it's an excellent place now, mostly because of Hannah Shamloo and Jordan Carey, our two new geology professors, who have been trying to feature on camera, Jordan most recently in a couple of field videos, and I'll try to get Hannah on camera as well because they are our future for sure. One final wrinkle For the first time, we're trying to amplify the speaker in the room. Right here. So it's an experiment. We'll see how it works. Our speaker is going to be anchored there, and she's going to have a mic that's like on her mic stand that's going to amplify her voice for you, and that big Muppet-looking microphone is for the room. So that's the tweak. Can we get the speaker's voice to be amplified in the room? Because I've given up on the sound system in the room, even though it's a new building. Okay, well, good. Let's turn the camera around. Thank you so much for joining us. Can I ask one more time? Can I ask one more time? In fact, I want to ask up there too. I'm gonna double check the mic here. Home viewers, I'm checking the microphone. Can you tell me 5 by 5 home viewers that you can hear this microphone, which is our experiment for today? 5 by 5 Muppet microphone. 5 by 5 Muppet. So it's like 2 lapel mics and a Muppet mic all right here at the same place at the same time. All I see is 5 by 5, but I think you're talking about that one as well. Speaker mic. Okay, thank you, Brian. Okay, great. Thanks. We'll start in a few minutes. Housekeeping. Okay, feeling good?
Mm-hmm. Yeah.
Okay, great. Yep, we'll get started in 5 minutes. Okay, thanks. Hello. Hi.
Hi. How are you?
Good. You?
Good.
You got time to talk afterwards?
I'm talking to a potential student who is actually Rebecca Springer, who's thinking of coming back for grad school at 2, but after that,
Okay.
wait, no, at 1.
At 1?
So at
Okay.
2 or before, when I'm done with her, will you be around?
Yeah, I think so.
Okay. Shall I just come down?
Yeah, let's try that.
Okay.
Nothing much. Just
Yeah.
you know what I want to talk about. Yeah. Thanks.
Still like you as a person, he's like like just because I have
Yeah.
comments. So it's like, what are these gonna say?
What is it gonna say?
I got so scared.
Why would you go up this road to map? What is wrong with you?
This is so dumb. Why would you? No.
Basalt? What the hell?
Hi. Are you okay if I announce 4 o'clock Fidelina's, the Mexican place?
Sure. Did you find out any more about that? Or did you talk to Hannah about that?
Hannah sounds like a good idea, and
All
we
right.
haven't gone beyond that. But I think that's what we're going to try.
Okay.
Okay.
Yeah.
And we'll just open it up to whomever wants to come.
Yeah.
Okay.
Sounds good.
And after I welcome everybody, you're going to interview her at the mic. Are you going to introduce her at the
I'm
mic?
not going to interview her.
You can interview her too. Ta! How's it going, man? Good.
I got you.
I'm just trying to pick up.
Hello, Nick fans. It's your favorite rock liquor, the one and only.
Look into the camera. You want to say some final words? This is the state of a union.
It's, I'm passing away after this. I don't know. Who's gonna miss me?
Maybe sand.
What sand? I have
The
rock.
better you charge.
Yeah, if you can shovel it out. It's all yours. It started growing roots in there, probably.
Should have gotten an just for the bed of your truck.
Okay, we're going to start. That clock's like 3 minutes slow, I just noticed. So it's already afternoon, so I'm going to get us going. Okay, everybody, welcome. Welcome. Hey, man, happy end of the school year. This is our last talk of the year. Thank you so much for being here on such a beautiful day. Looks like we've got people still coming out of Volcanology Lab, so they'll be continuing to trickle in. How are we doing with the Vindmans? Is there still plenty? Yes. Please, please. That's going to go to waste otherwise. Get up right now. There's plenty of Vindmans. Come on, I'm serious. There's plenty of cold drinks in the cooler. There's still some coffee left. It's going to take us a couple minutes to get settled anyway, so don't be shy, please. Hannah and I are continuing with this speaker series. We have a whole set of plans for next year that will be slightly different than what we have now, but we have a good thing going, and it's been so great to have you with us for so many of these sessions. So I hope you enjoy the summer, and I hope to see many of you back in the fall. We have one experiment happening today. So there's a new microphone that is intending to project the speaker's voice into the room, not using these ceiling speakers, which are garbage, but Nat brought in his own speaker that works with this Nerf-looking mic there. So our speaker today will be standing at that mic, and we'll see if that works. There'll also be a smaller mic that goes to the home crowd. So that's the experiment for today, but we continue to tweak with this whole thing. But hey, man, it's working, and thank you so much. So no future talks to announce. Can we thank Vindman's Bakery for all the wonderful treats this whole series? Help yourself. There's still plenty, okay? Great. So Walter invited our speaker today. Let's have Walter introduce the speaker, and then we'll get started with Lucinda.
You can clap again if you want. Look at
Oh!
So I'd like to introduce Dr. Lucinda Leonard. She's from the University of Victoria in British Columbia. She did an undergrad at Trinity College Dublin, and then did a PhD program over at the University of Victoria in British Columbia, and hasn't left. She's done all sorts of really neat projects, from GPS up in the Yukon Territory. Early on, she was doing GPS here on the eastern part of the Cascades with Rob McCaffrey, and she's going to talk about her current work on faulting sources and tsunami sources in the Salish Sea. So, take it away.
All right, Lucinda, thank you.
Well, thanks so much for having me here. It's a pleasure to meet you all and to share some of the work we've been doing a little bit up to the north of here. I'm drawing on the work of many, many other people here, more than even are listed, and particularly a couple of past graduate students, Megan Caston and Fatima Namadi, so I'll be highlighting their work later on. My title here, Head for the Hills, it's a little bit tongue-in-cheek. And this was in response to some of the media coverage of our recent paper on the Hulaklik Elk Lake Fault, which is shown, or a paleoseismic trench, trying to find the right button for the laser, there it is, paleoseismic trench across a fault scarp here just north of the city of Victoria on Vancouver Island, where I live. And we found evidence here of an earthquake about 3,000 years ago. And although this work was onshore, we're at the shore of the lake here, the fault likely also continues offshore, or rupture might jump to other faults. And so there is the potential for tsunami to be generated, likely just a few meters in height, although that could certainly be locally damaging to Victoria. But some of this got picked up by the media as, I don't know who came up with this map, but apparently you're safe here, but only just about. So I had to make sure to put this label on so this doesn't get shared further. Fake news. Here is that Hulaklik Elk Lake Fault, as I said, could produce a locally damaging tsunami, but you certainly do not need to head to the mountains. And even the mountains, according to this map, would not be safe enough. But I hope by the end of this talk to convince you that if you spend any time on the shorelines of water bodies in this region, and for the Salish Sea, I'm referring to the Strait of Georgia, Puget Sound, and the Juan de Fuca Strait, although most of my talk will be focused on kind of eastern Juan de Fuca Strait and the Strait of Georgia. We certainly have lots of experts here on the southern area. If you spend time on the shorelines here, you do need to be ready to get to higher ground. It should be top of mind on the coastlines and the shores of lakes. Okay, so just back to basics. What is a tsunami? It's not one single wave, but a series of long wavelength, long period waves. And a tsunami wave can typically have hundreds of kilometers distance from the crest of one wave to the next. So much, much longer than a wind wave. And it can be sometimes many hours from the arrival of one wave to the next. So, and these waves are generated when a large volume of water is displaced. Typically that happens from underneath during a subduction zone earthquake when the seafloor is offset vertically, lifting up that body of water over top. It can also be generated by an underwater landslide, or the displacement can happen from above, from a landslide into the water, or an asteroid impact, volcanic eruption, and so on. And we're quite familiar, unfortunately, with scenes of large tsunamis over the past couple of decades. Here's an image from the 2011 tsunami arriving at the coastline in Japan. And so we're aware that it doesn't always appear like a big wall of water, but sometimes like a tide that just keeps on coming and keeps on rising. And we're also only too aware of the sometimes catastrophic impacts of these tsunamis. Here's a selection of major tsunamis from the last 20 years, most of them generated by subduction zone earthquakes. Here we've got the max run-up, the max height that the tsunami reached to, and number of fatalities. So typically, the size of the earthquake scales with the size of the tsunami and the corresponding impacts. So why are tsunami waves so dangerous? Well, they involve not just the upper part of the water column, like a wind wave, but the entire water column. And of course, that massive wavelength means that there's a massive amount of water involved in each wave. The speed that a tsunami wave travels is proportional to the water depth. So they travel fastest in the open ocean, hundreds of kilometers per hour. But as that wave approaches the coastline, gets into shallower water, the wave slows down and then begins to kind of pile up on itself. Just a few definitions in here. So we're measuring everything relative to the water level at the time, or the state of tide. We've got wave amplitude, so the height above that tide level, wave height, so the distance from the peak to the trough. The run-up here is now the highest elevation reached by the water when it gets up onto the land above the state of tide. The flow depth is probably what matters to you when you're standing at the coastline. How high is the water relative to the ground? And here we've got the inundation distance. How much a tsunami will run up depends, of course, on how big the tsunami was that was generated in the first place, but also on other factors like the directionality of the wave, the shape of the seafloor, the shape of the coastline. And it's also important to remember that it's often the first arriving wave. It might not be the largest one. There might be a bigger wave coming. So you need to wait several hours to make sure that the danger has passed. In terms of what size tsunami do we need to worry about, these numbers might seem pretty small, but we've just looked at why tsunami waves are so dangerous. And even for tsunami amplitude or run-up, only 0.5 meter, that can be a tsunami that has really dangerous currents and can cause damage. So that's kind of our threshold. But we are going to expect some more widespread impacts once we get above the 1.5 to 2 meter mark. Just bear those numbers in mind. So how does a subduction zone earthquake generate a tsunami? Here we've got a schematic of a subduction zone. And so like the Cascadia subduction zone, where the Juan de Fuca plate goes underneath the continental North America plate, and the oceanic plate just keeps coming along it like a conveyor belt, feeding in here, but the seismogenic zone is locked due to the frictional properties here, and this causes the upper plate to kind of get dragged down and bowed upwards along its edge. And this is an indication when we can measure what's happening at the coastline in this part of the world, or further to the west, where we can measure this gradual uplift, telling us that this subduction zone is locked offshore, and we're also getting pushed, or the west coast is getting pushed to the northeast. So we're building up strain towards the next big earthquake, and of course, eventually, the friction will be overcome. That leads to rupture, and also notice that while the coastline area was going upwards, the seafloor area was getting dragged downwards. When that reverses, of course, we have sudden uplift of the seafloor and an absolute mountain of ocean water, sorry, back one, that is lifted up and starts a tsunami. We are, of course, our local subduction zone is the Cascadia subduction zone, and this is the dominant source of tsunami hazard for this part of the world, for the west coast. We know that the last large earthquake here happened in the year 1700 on January 26th, and we know that from this orphan tsunami that showed up in Japan, where the Japanese did not feel an earthquake prior to arrival of that wave. So a bit of a detective story to figure out where did the tsunami come from, although all along there were indigenous oral histories from Vancouver Island down to Northern California that told of the events of the night of January 26th, although the timing of the stories was constrained to a few decades. Here's an example from the Hwayat First Nation on west coast of Vancouver Island. It was at nighttime that the land shook. They had practically no way or time to try to save themselves. A big wave smashed into the beach. The Pechina Bay people were lost. And many other pieces of evidence going into documenting the evidence for that 1700 earthquake, including evidence that the coastline dropped down suddenly during that event, that the tsunami brought in sand deposited as a layer in coastal marshes. We've learned a lot in recent years about the structure of the subduction zone. The three images here are kind of three potential rupture scenarios for a big earthquake on the Cascadia subduction zone, and the colors are corresponding to the maximum tsunami height for each one. Won't get into the details here, but one has a buried rupture, one involves a splay fault, and the other involves slip all the way to the trench. But if we focus in, clearly this is a major concern for the outer coast and the heads of the inlets. But in the Salish Sea area, much of that area is relatively sheltered. So somewhat sheltered. Also importantly, it's going to take time for that tsunami wave to arrive to many parts of this area. Arrival times mostly more than an hour. We also actually have another nearby subduction source that spawned a tsunami in October 2012. Haida Gwaii here up to the north. Here's Vancouver Island, there's Haida Gwaii. And although this is dominantly a strike slip plate boundary up here, there is a component of convergence, and that's what we saw in this earthquake. And here we've got a zoom in of the west coast of Haida Gwaii. Here's the rupture area shown offshore the western part of the islands. And you can see that the effects of that tsunami were really quite localized to the west coast of Haida Gwaii, where thankfully there was essentially nobody in the way. It's very remote. Most people live on the eastern side of the islands. But there was some concern raised when this wave was picked up heading towards Hawaii, that it wasn't too big by the time it got there. Here I am in the forests of Haida Gwaii, documenting the effects of that tsunami, which were in the form of logs that had been picked up and floated around. And we found sometimes just a footprint of a log where there had been one, and now it was full of seaweed. And we found seaweed hanging up in the trees up to 2.5 meters above the ground. Maximum run-up was at this location 13 meters above the state of tide, close to 40 feet. Trying not to go off on too many tangents here, but happy to talk more about that if anyone has questions. We also, of course, have in many people's living memory impacts of the 1964 Alaska tsunami, which caused major damage to the outer coast and at the heads of inlets. These photos are from Port Alberni, which looks like it's inland, but it's at the head of this long inlet where tsunamis tend to amplify as they travel along it. Looking at this particular model here, we can see that most of the Salish Sea area would be relatively sheltered from an Alaska-type tsunami, and that was the case in '64. I also mentioned that tsunamis can be caused by landslides. An extreme example is the 1958 Lituya Bay tsunami up in Alaska. This was a massive rock fall at the head of the bay here that was triggered by shaking in a massive earthquake on the Fairweather Fault that runs close to here. And that massive slab of rock went down into the water, washed up over 500 meters on the other side, and stripped away trees from all around the edge of the inlet. And the tsunami had enough power to strip the barnacles off the rocks. The Tlingit know that this is not a good place to spend time. This is not an isolated event, but these happen periodically. And it's incorporated into their stories as the sea monster Ka Lituya, who, when he gets displeased, he lives under the bay, and when he gets displeased, he reaches up and takes hold and gives it a good shake. Compared to tsunamis triggered by earthquake seafloor displacement. Landslide tsunamis have a much shorter wavelength. They have this capacity for extreme run-up, but that tends to be quite localized because these waves will dissipate quite quickly. Landslides, tsunamis may arrive with very little warning or even no warning. Sometimes they're triggered by heavy rainfall. It's not always an earthquake. Okay, getting to the point. What about local sources? I've looked at all these other sources that are potentially, not too big of a deal in most of the Salish Sea. So it's the outline for the rest of my talk here. Focus a little bit on the tectonic setting of the area. Then we'll look at some evidence that we've gathered from onshore faults, mainly from Vancouver Island. Then looking into some constraints on offshore faults, focusing on the southern Strait of Georgia. And then I'll show you some results of tsunami modeling of various rupture scenarios and a potential landslide tsunami. So the Cascadia subduction zone dominates the tectonics of the region. We're looking at part of the lock zone here offshore Cascadia. And these arrows are showing GPS vectors relative to stable North America. So we have subduction of the Juan de Fuca plate beneath North America at about 4 centimeters per year. And that relative motion is quite oblique. It's not perpendicular to the trench. And that obliquity decreases as we get actually into the northern part of southern Vancouver Island. Now, that margin parallel motion, or relative motion, is partly transferred to the upper plate, and we have motion of the forearc northwards. So you have the Oregon block here moving northwards, which can be described as clockwise rotation about a pole around here. And this northward motion then is accommodated by a lot of north-south compression in the region of the Olympics. And in this model by Wells here, we have the kind of end of this deformation marked as, we'll be looking later at the Leech River Fault that runs across here. And the idea is that got the Canadian Coast Mountains up here, the strong Canadian backstop is stopping the deformation, and this northward motion is crumpled up against it. And that is our model essentially here on the top here, this northward motion stopped by this Canadian backstop, and we'd expect that we'd get thrust faulting around the Leech River Fault, taking up that north-south shortening. If we take a look at the vertical axis rotations from the GPS velocity field, all these blue shapes here are showing us clockwise rotation happening south of the Olympic Mountains, but it actually switches to counterclockwise rotation on the north side, implying that there's some kind of bending happening around the Olympic Mountains. And we see evidence for this switch from clockwise rotation to counterclockwise rotation in the paleomagnetic declinations that also indicate this switch from clockwise to counterclockwise across here, indicating that there's oroclinal bending happening around the Olympic Mountains, and it's been going on for a long time. And this would also predict, really strong shortening in the Olympics, compression across the Seattle Fault, and so on. And it also predicts that we would get right lateral transpression on the northern limb of the orocline and left lateral transpression on the southern limb, which is what we see from paleoseismic and other constraints on the faults in the region. This work here came out of actually the honors thesis work of Theron Finley, who's now a PhD student at UVic. So we're certainly seeing a lot of seismicity concentrated in these more southern latitudes, but we do see that earthquakes just don't stop. They keep going in the crest further north. And there's been some quite significant earthquakes. It's a little bit off the map here, but this star is marking the epicenter of the 1946 magnitude 7.3 earthquake. This was an oblique right lateral event. is onshore, and it caused many, many landslides. And some of those landslides generated tsunamis, one into a lake on Vancouver Island, and another one offshore the east coast. And that landslide tsunami led to the one fatality in the event in Canada. There was actually a heart attack death in Seattle from that same earthquake. There's also some interesting clusters of seismicity further north, including this cluster right around here, where the earthquakes define a north-dipping reverse fault plane there. So certainly a larger earthquake on a fault like that could be tsunamigenic. So we know we have large events. How do we get an idea of how often they occur? One record we have is a record of debris flow deposits in the Saanich Inlet, close to Victoria here. There's 18 deposits since about 4,000 years ago. The youngest actually correlates with the 1946 earthquake. And about half of these deposits can be tied to the timing of megathrust earthquakes, but the other half have unknown sources, but likely mostly crustal fault earthquakes. So we're looking at a just under 500-year recurrence of non-megathrust related strong shaking in this area. And that matches with what we see in the statistics of the seismicity from the yellow box here. So we know that the frequency of the more frequent smaller earthquakes can help predict the frequency of the much larger, more impactful earthquakes that we don't have a good record of, making some assumptions about what's the maximum size you could get for a crustal earthquake in this region. This is work by my PhD supervisor, sadly passed away last year, Roy Heinemann. And this gives us a recurrence for earthquakes exceeding magnitude 7 of about 400 years. So we know that there's potential for large crustal fault earthquakes, and some of these run beneath the Salish Sea. We also, of course, have evidence from tsunamigenic earthquake on the Seattle Fault about 1,100 years ago that Bree and others have worked on. And so we knew we needed to be concerned about crustal fault sources. I started working on this problem about 15 years ago as a postdoc with the Geological Survey of Canada. I'd had a back injury doing GPS fieldwork on northern Vancouver Island. Couldn't do fieldwork for a while, and so I was tasked with completing a preliminary tsunami hazard assessment for Canada. So a pretty big task, learned a lot, but I wanted to figure out how to account for crustal sources, but without really having many constraints on the faults. So this map is just showing this is prior to 2017, although this map is mostly from 2001 with the addition of some faults in the north from 2012. But at this point, only the Devil's Mountain Fault here was mapped to actually cross the border into British Columbia. We see the Leech River Fault and San Juan Fault on here, but to this point, prior to 2017, they didn't have good evidence that they were active today. So my method was to use the statistics of the seismicity, make assumptions about how much of that was in the submarine area, make assumptions about how much of it would be reverse faulting, and use empirical relationships between the earthquake magnitude and tsunami impact to come up with approximately 2,500-year recurrence of quite significant tsunami impact in the area. I won't get too much into the detail, but it certainly indicated that crustal faults might be more significant for tsunami hazard for many parts of the Salish Sea. So we've learned a lot since 2017, largely through the availability of LiDAR data in BC, and the work on Vancouver Island, largely driven by my collaborators, Kristen Morel and Christine Regala and their students. So we've identified that the Leech River Fault is in fact active. We have evidence for 3 earthquakes in the Holocene from some paleoseismic trenches. We've recently, as I've mentioned right at the start, found that this Hulaklik Elk Lake Fault is active. We have evidence for one earthquake. The Beaufort Range Fault up here, likely the source of the 1946 magnitude 7.3 earthquake. PhD work of Emerson Lynch, working with Christine Regala. We dug a paleoseismic trench across that and discovered evidence for 5 large earthquakes in the Holocene, and really quite a significant slip rate on that fault. Lots more lines here in BC offshore. Notice this is a preliminary map, but it was useful to kind of show the extent and the different areas where we found evidence of faulting. But the San Juan Fault, we still don't have clear evidence that it is active. Still kind of poking around in this region to see if we can find that evidence. A little bit on the Leech River Fault. So these studies are onshore, but it's very likely that this fault runs offshore as a show. So we can learn about the rupture mechanisms from what we learn onshore and potentially apply them offshore. The Leech River Fault, originally a terrain-bounding fault with the accretion of the Crescent Siletz terrain to the south, accreted to the earlier accreted Pacific Rim terrain. And this map below here, the dashed line here is marking the bedrock contact between those two terrains. And in red here, we've got Quaternary cover on top, and in red here, we've got identification of topographic scarps from the LiDAR data. So we can see that they're, approximately close to that bedrock contact, but not exactly coinciding, and they're kind of discontinuous, form a fairly wide zone, but they can be on either side of that older bedrock contact. We have trenched the fault in a couple places. Over here, close to the bend in the fault, and a few kilometers further to the east. So we'll just take a quick look at what we've learned there. So this first trench site here, beautiful LiDAR image with a till surface here with a colluvial apron on it, and a very clear scarp that is uphill facing. So this photo here, we're actually overall looking downhill, but then you're stopped by this scarp here. And so this was the location of the first paleoseismic trench. Now, each time you have an earthquake that forms a scarp, it makes a step in the landscape, and over time, that scarp is going to become less steep as material diffuses and makes a little wedge at the base of the step. It's called a colluvial wedge. And so when you dig a paleoseismic trench, you're looking for these colluvial wedges, and if there have been multiple earthquakes, then you'd expect multiple wedges. So this trench had evidence for 3 colluvial wedges, 3 earthquakes since 9,000 years, taking samples to bracket the age of the earthquake from what was deformed before or after each event. So we have evidence at this particular site for only dip-slip motion, near vertical fault, about 1 meters of slip per event. Further to the east, not that far along, a different trench reveals evidence for 1 earthquake, and this one had some evidence for right lateral slip, as well as some oblique motion, or some dip-slip motion. Now we're moving to the coastline, and some evidence that the fault does indeed continue offshore. This is a seismic reflection profile run along a spit here at the edge of Esquimalt Lagoon. And we see, again, a fairly wide fault zone, near vertical discontinuities that continue from the bedrock right up through the Quaternary sediments. And even further offshore here, again, these near vertical discontinuities, likely the Leech River Fault continuing over, and this association of these faults with bedrock topography. The signature of seismicity seems to be continuous from the Leech River Fault over to the Devil's Mountain Fault. Each of these profiles is kind of north-south successively along here. Our evidence from the trenches is that it's the fault dip must be near vertical, near surface, but then it seems like it must decrease with decreased down dip, so overall about 60 degrees dip. Got some earthquake mechanisms in here, dominated by right lateral transpression. Now, interestingly, both the Leech River Fault and the Devil's Mountain Fault have an older history of left lateral strike slip, and now we're seeing this evidence for right lateral. Here we've got results from sites, paleoseismic data from both the Leech River and the Devil's Mountain Fault. Overlapping age ranges, so potentially some earthquakes do rupture from one fault right through to the other, which would make for a much larger earthquake, potentially up to magnitude 7.5. Both faults, or maybe the same fault, has a rupture style that varies along strike, but mainly dextral transpression. Devil's Mountain Fault, of course, has a very large section that is under water, and so dip slip on that fault would likely produce a tsunami. And we might be looking at recurrence on the order of a few thousand years, up to maybe closer to 7,000 for these really big events. And Bree was showing me lots of work that she and her students have been doing around this region, finding various potential tsunami deposits, and she's actually run some modeling of potential tsunamis in here. So I'd definitely like to see some more of that. So here's that Leech River Fault, Devil's Mountain Fault, dips northwards underneath the city of Victoria. And now we're going up to the Hulaklik-Elk Fault, which dips southwards under the city of Victoria. So we're right sandwiched in there. And again, this fault was identified through LiDAR data. And here, so this is going right across the Saanich Peninsula. Again, the bedrock contact, lots of evidence of bedrock scarps. But of course, we need to find younger sediments that are offset in order to indicate that the fault is actually active, or active in the Holocene. Over on the eastern side of Elk Lake here, we have a scarp that is developed in Quaternary sediments. This is a drumlinoid feature here. And so right on the shores of Elk Lake, also known as Hulaklik by the Saanich peoples, we decided to dig a paleoseismic trench. And here's an image similar to the one I showed at the beginning. Partway through this work, we actually found some older aerial photos. This one's from 1926 that showed the scarp was much more prominent in the past, before there was a lot of anthropogenic modification here. They actually worked to fill in the beach here at Eagle Beach. We found actually a lot of anthropogenic material on that side of the trench. The scarp here seemed like it was actually formed by a fold in the hanging wall of a thrust fault, where the thrust fault didn't quite rupture all the way through to the surface. And a lot of the faulting that we identified in the trench was actually little extensional faults in that anticline. But at the base of the trench, we did uncover shallow dipping reverse fault, or a pair of them here. So consistent with the south side here being lifted up over top of the north side. I had an honor student do some resistivity profiles. This actually wound up being exactly where we dug the trench here, but this was a few months prior. And I'll just jump down to the bottom one here. The black line here is showing the eventual footprint of the trench, that low angle thrust fault that we uncovered, and the geophysics is telling us that it must get quite a bit steeper immediately below the trench here. And we see this is an artifact here from a drainage pipe, but if we look at the contact between this more conductive material over top of more resistive material, there's an offset. The material on the south side is close to 3 meters higher than that contact on the north side. So consistent with the sense of motion indicated by the scarp. So some constraints on hazard for this fault. we don't know. We did find evidence of the fault on the other side of the lake. Likely it also might continue across Saanich Inlet. And we've also got some evidence of faulting offshore in Harrow Strait. One of these faults might continue with this one, to be determined. But depending on how long of a rupture, we are getting up into potentially magnitude 7 range. And with potential for tsunamis to be generated in 3 different water bodies, Elk Lake itself, Saanich Inlet, and in Harrow Strait. But lots more to be determined. So we haven't carried out any tsunami modeling for these faults. Not yet. The past few years, some of my focus has been further north. I'll just get you oriented here on this map. So City of Victoria down here. The northern end of the peninsula is Sydney, the location of the international airport, ferry terminal, and that is going to appear at the bottom left of the next map here. So here's Sydney again. And then here's the Canadian-US border, zigzagging its way through up into Boundary Bay. And our efforts focused here thanks to a project that was focused here, a West Coast case study for a project called Coastal Flood Mitigation Canada. Many different partners led by Natural Resources Canada. So this was an opportunity to model all kinds of sources of coastal flooding in this region. So they modeled storm surges, modeled tsunamis from Cascadia sources, Alaska-type sources, and I had a student, Megan Caston here, work on the potential for crustal faults in this region to generate tsunamis. So Kelsey et al. In 2012 had identified 3 active faults on the south side of Boundary Bay here. I'll just focus on the ones that have more likely tsunamigenic potential, the Birch Bay Fault and the Sandy Point Fault. Birch Bay Fault has evidence for 1 paleoseismic earthquake with a possible tsunami deposit, and there's evidence that the north side is uplifted relative to the south side from a variety of different data. And then here the Sandy Point Fault, also north side up, and evidence for 3 paleoseismic earthquakes. There's also another fault that has been identified as active, this one by Green et al., 2018, the Skipjack Island Fault Zone. This one is mostly offshore and identified through both the seafloor bathymetry and from some shallow seismic reflection, with evidence of offset of Holocene age sediments. We don't have any paleoseismic event constraints, how much slip per event on that fault, but lots to work with here. And so Megan was tasked with coming up with some scenarios on these faults, and she also tried to identify if these faults may continue further to the northwest, and that would, of course, would increase their tsunamigenic potential. So she looked at whatever data she could get her hands on. So crustal seismicity in the region here. I previously pointed out that cluster of earthquakes with the north dipping plain up here. There's another quite interesting cluster of earthquakes south of Point Roberts here. That interestingly looks like it might be a long strike of the Sandy Point Fault. Otherwise, fairly scattered seismicity, lots of uncertainty in the locations. But it's something to go on. And Megan looked at profiles of the seismicity, so projected onto this profile here that crosses these 3 faults here. Knowing the location of the trace at the surface, she came up with some rough constraints on north dipping fault planes. So with north side up motion, there's also evidence of folding associated with these faults, so indicating that that dip slip is compressional. And so we expect that northeastward dip for these faults, at least the first 2. And so there's her dip constraints. And there's also some constraints on likely rupture mechanism from SH max, so the horizontal direction of maximum compressive stress, or maximum horizontal direction, from inversions of earthquake mechanisms. So by looking at the orientations of that stress direction relative to the orientation of the faults, this is an indication that we expect, again, right lateral transpression on these structures. It might be partitioned between different structures. One of the pieces of evidence used by Kelsey to map out the traces of the Birch Bay, Sandy Point, and Drayton Harbor faults was aeromagnetic data. So he had this data set shown in the lower right corner here. And in order to isolate anomalies that likely had shallow sources and that might reflect offsets on near-surface materials, he isolated the high-frequency part of the magnetic anomaly data and identified that both the Birch Bay fault and the Sandy Point fault had these positive to the north magnetic anomalies that are consistent with north side up offset. And what Megan did was she found a larger but lower resolution data set available from Natural Resources Canada, and she applied the same processing steps to that data so that to see what could these anomalies potentially continue further to the northwest. There are difficulties once you get offshore. Now you're dealing with trying to preserve these magnetic anomalies, and there might be a lot of sediment reworking. We're starting to get into a thick pile of Fraser Delta sediments here, so there's that issue. And then also some contamination, a big, huge anomaly here from a power cable that goes across the strait here. And then, as I said, lower resolution data. But one of the things that she was looking at. She also found fairly late in her degree, she found some seismic reflection data. So she took a look at that. There's one deep line here that goes potentially across the potential extension of the Sandy Point fault. So we'll take a look at that one next. So this is the north end and the south end. And she's also projected onto that profile the seismicity and earthquake mechanisms here that we're now looking at in side view. I should also point out on the previous slide here, in pink here, these little dots, so an area of pockmarks that were identified in the seafloor by Green et al. Now, finding a linear stretch of pockmarks is often an indication, or maybe an indication of faulting, because faults are often conduits for fluids that sediment is then expelled as the fluid is expelled into the water column and leaves a pockmark. So that location is down here. Now she noticed that this Point Roberts cluster of earthquakes actually might be two separate clusters, where the shallower cluster may link up with an extension of the Sandy Point fault, but the deeper cluster would project, if we look at the fault planes of the earthquake mechanisms, would predict further to the south, and it actually seems to line up with the location of the pockmarks on the seafloor, and there may also be some dipping reflectors in between. So potentially another fault identified subparallel to these ones. She also found some recently digitized shallow seismic reflection data. I'll just point out on the previous image here, this is down to about 15 kilometers in depth. You're not getting a lot of detail on the shallow subsurface. For that, we need this shallow seismic reflection, but there's still quite a bit of seismic attenuation because of fluids trapped in these delta sediments. But she noticed an association with where the Sandy Point fault had been mapped offshore. There seems to be kind of a valley, a buried valley feature that might be associated with the fault. So perhaps some fault-controlled older seafloor topography since filled in. And she found similar or larger features for this postulated Fraser River Delta fault that she's mapped in here. So potentially, as well as trying to use the magnetic anomaly data, the earthquakes, getting what information she can to potentially trace out extensions of the fault from tracing these features in seismic reflection data. Now down to the Skipjack Island fault zone down here, and some shallow seismic reflection, some really large localized offsets of the seafloor, large scarps and displacements of Holocene sediments. So Holocene north side offsets, evidence from rock outcrops on the seafloor implies strike slip deformation, more consistent with left lateral, but of course that could be an older history. The SH max directions in the area, again, would indicate likely dextral transpression for this fault. It may have more of a strike slip component than the other faults, but this was another source for Megan to model. So here's her new fault map, lots of dotted lines where things are much more poorly constrained. Given all the uncertainties here, for her model, she kept them pretty simple and tested different scenarios, both short and long ruptures on all these faults, but incorporating more detailed structure where we have better constraints on the trace of the Skipjack Island fault zone. So Megan's task was to constrain these various scenarios and then model what would happen to the seafloor during one of these events. And the vertical displacement of the seafloor would then be taken as input for a modeling of a tsunami generated by each scenario. So we'll just take a quick look through some of these rupture models. And she's testing, so from the paleoseismic constraints, this is the Birch Bay fault rupture scenarios, both the short ones and the long ones. And the uplift might have been as low as 0.5 meter in an event or up to 2 meters. The red areas are uplifted, green are down, and the blue arrows are showing the horizontal displacements, assuming in this case pure reverse slip. And we passed those surface displacements over to Reza Amuzgar at Ocean Networks Canada to model the resultant tsunami. Just shown 2 examples here, a short rupture case and a long rupture, both involving the maximum slip, maximum uplift of 2 meters. And here we've got focusing on this case study region of Boundary Bay. And notice the different color scale here in the up one, for the short versus long. This one goes up to 5 meters. And we can see that, so obviously the longer rupture, it has a much larger tsunami impact. There's a lot more inundation and wave heights over 3 meters in much of this area. These are, I guess, wave amplitude above the state of tide. Run-up could be larger. It's often up to double the wave height. Just quickly looking for also, so the Sandy Point, again, short and long. And let's look at a couple of the tsunami models here. Again, this scale maxing out at 3, this one at 5 meters. And Reza also played around with different reference frames. So this one was at a higher starting tide, and also looking at, well, what if this happens when there's been 1 meter of sea level rise, which is going to make the inundation much worse. So kind of an extreme scenario here, but really significant impact. A lot of low-lying areas here. And I didn't point out on the right here, we've got the maximum currents speed as well. So really, really significant. These numbers we're looking at over, I think I have the wrong scale in this upper one, but certainly getting into the 10 meters per second in some places. So really, really high potential for damage. A couple models here for skipjack. Of course, we have no constraints from paleoseismic events, so we don't know how much slip to make per event, but we can get an idea based on estimates of how big of an earthquake we could expect and use scaling relations to get an idea of the slip. So that's what she did here. And we include more of an oblique component to slip in the Skipjack Island. Seems to be probably more strike slip, but and then we fed over the vertical displacements to Reza to model here, and this scale going up to 3 here, so still quite significant. But the largest the largest Sandy Point fault tsunami is the biggest of all of these. Now the location of the Skipjack Island fault zone here is very close to the northern end of Orcas Island. if I have a better zoomed out map. No, I'll have to go way too far back. Okay, Boundary Bay is up to the north. And this is kind of the eastern part of the Skipjack Island Fault Zone. And there's been identification of landslide deposits on the seafloor adjacent to this very steep coastline of northeastern Orcas Island. And so again, part of this Boundary Bay project, we wanted to include a landslide source tsunami, and so this was the task for Fatima Namadi, just recently finished her PhD, graduating in a couple weeks. And she modeled a subaerial landslide, kind of taking a worst case scenario, the full length between the deposits, the full extent of the deposits on the seafloor, and modeling what would happen. And of course, a potential trigger for this kind of failure would be strong shaking from an earthquake on one of these nearby faults. Won't get into the details, but she constrained all the various parameters, modeled how the seafloor would change, and when she sets the model going, the failure would move over 700 meters in total. Now we're going to take a look at an animation of the wave. These various boxes on here are showing areas where we had higher resolution bathymetry and topography data. So really important to get really accurate measurements of, or accurate predictions of the tsunami impacts. But the animation here I'm going to show you is from actually the coarser grid, just so we have a more zoomed out view. This is going to max out at 5 meters. I'll show you a time series in a little bit from an area very close to the source region to show you really how high the wave got. And I didn't test this here. Let's see if I just click, if that'll work. Oh, that's our time series. I gotta find, here we go. Hopefully this works. Oh, I got it going and then stopped. Okay, so we have propagation to the north. Reds are above tide level, and then the troughs are behind it. And here, of course, we're focusing on how big could this be in Boundary Bay, and it certainly has dissipated quite a bit, even over that short distance. I'll just bring up, but still quite significant waves on the southeastern part of this area, getting into Lummi Bay. I will bring up now that time series from a location very close to the source region. Initial wave is almost 20 meters in height. Then we have a trough that's deeper than 10 meters below tide level, and then these high frequency waves. After an hour or so, it's really quieted down quite a bit. Fatima then worked out the run-up all around the area of Orcas Island, but also the Boundary Bay region. So here we've got the maximum run-up up to 30 meters close to the source region. And this little Clark Island here would essentially be overtopped by this wave. Still some pretty significant impacts, close to 7 or 8 meters. Neptune Beach here, and lower, but still significant run up, and the graph shown below into Boundary Bay. Okay, so just focusing on this area, so a relatively an area of the Salish Sea that's potentially relatively sheltered from any tsunamis. Well, let's just compare the results of these various models. So starting with the modeling of the 1964 Alaska earthquake, and I've chosen to show a time series from approximately the same location for each of these studies. And the bars here, this is the tide level. This is 1 meter, 2 meters. And so it takes more than 5 hours for the first wave to arrive. It's got to travel all the way from Alaska, and then it doesn't quite reach even 0.5 meter maximum wave height. But it keeps going for many hours afterwards. Okay, now let's look at one of those Cascadia events, bigger. And over 2 hours for the first wave to arrive, and then you would have an indication here that something is going on, because the first sign is that the water would actually pull out. In this case, it's the trough that arrives first, and then we're getting up close to 1.5 meters at this location. Run up could be higher, so we're getting into that potential for some significant impact here. Okay, now our local sources. I just chose one of the crustal fault, one of the big scenarios on the Sandy Point fault. Notice this is the 0 hour point. You are right in the fault zone, so you don't have much time to react at all, and this would have a much more severe impact compared to these other more distant sources. So I've made all the vertical scales the same here, but they're different in the time scale. Finally, that Orcas Island, so we know it's really big, close to the source, at this location in Northern Boundary Bay. Not as big, but getting up close to 2 meters with one of the later waves. So this is a 2 hour time stretch. Notice here the really high frequency nature of landslide tsunami compared to the earthquake generated ones. So conclusion, locally sourced tsunamis seem to have a higher damage potential for many parts of the Salish Sea. Which brings me to some take-home points here. These local sources could produce damaging waves that would arrive with little or no warning. If it's triggered by an earthquake, you've got to take that shaking as your warning to get to higher ground. We've learned a lot, but we still have a lot more to figure out. We need to do a lot more modeling. We need to pay attention to these sources for mitigation and work on bringing these uncertainties down, particularly what is the structure and extent of these faults. The more we look, the more we find. What are we still missing? We gotta keep looking. And it's tough to get at the recurrence of these events in order to properly feed the hazard into probabilistic hazard assessments. Can we use geodesy to get a better constraint? Can we start to measure strain buildup on some of these smaller faults? I'll just end with a couple of slides here to these latter two points. We've got master student Anna Potter-Odeski. She's working on another fault a little bit further to the north, right offshore Metro Vancouver here, taking advantage of over 100 recently digitized seismic reflection lines. There's been a couple of new lines collected as well. Some other interesting lines of pock marks in the seafloor. And she's identifying, yes, that there's some near surface and sometimes surface rupturing faulting associated with these pock marks. So work in progress. Her photo here is beside a campaign GPS survey. This one is located just south of the main city of Victoria at this location here. Over the past few years, we've been working to expand our network of campaign GPS sites across Greater Victoria. Some of these sites have some data going back to the 1990s. We only have 3 continuous GPS sites here, which isn't enough to give us any information on these crustal faults. So it's going to take some time to build up a long enough time series to potentially tease out the signals from these smaller faults. Of course, we've got the Leech River fault running through here, and now the Elk Lake fault identified here. Hoping to see some preliminary results soon. We've got an undergrad student working this summer on some initial processing of the data. So shout out to Danny Irwin. And I'm right over time. Thanks for listening.
Okay, a couple quick things. Number one, at 4 o'clock today, Lucinda and some of us will be down at Fidalina's. We're trying a new venue. Fidalina's Mexican restaurant on 5th Avenue, close to the corner of 5th and Main, right by Hotel Windrow. So we'll see you at 4 o'clock if you want to join us then. It's after 1 o'clock, so if you have to slip out, please do so quietly. We're going to do a few question and answers as a group, and Lucinda's going to try to remember to repeat your question so that the home viewers can hear it. Questions for Lucinda, please.
Right in the back.
Thanks for an awesome talk. Returning to the Elk Lake Fault Trench slide, were you able to support or rule out any strike slip motion?
Great question. The question was about the Elk Lake Fault and the work we've done. Were we able to determine or rule out any potential strike slip motion? Short answer is no. We think likely there is some strike slip, but it's difficult to capture strike slip with a paleoseismic trench unless you set it up properly. Yeah, we think it's likely, but yeah, we could not rule it in or out.
Was it the end of the quarter? We're out of questions?
Everyone's tired. Yes.
First off, very fascinated on the research we're doing in the region. I'm curious about what analysis you did on paleo-tsunami sites and detection thereof.
The question was, have I done any analysis on paleo-tsunami sites? What types of analysis? I have not done much on paleo-tsunami sites. I've mostly just looked at other people's reporting of that. That's the short answer. There is quite a bit of work being done to try to find evidence. Paleo-tsunami deposits. Bree showed me a ton of data for potential tsunami sites closer to, in the Puget Sound region. When people have gone out looking, yeah, there's not a lot that's been found on the Canadian side. Yeah.
One more? Kirk.
Are these faults forming because of the compression of the clockwise rotation?
Well, we're on the north side of this Olympic orocline, but likely there's still some compression that's happening further north. But the geodetic data is telling us there's a switch into more counterclockwise rotation, and I didn't explain very well why we. So the Olympic Peninsula coincides with a bend in the subduction zone, and it also coincides with where the subducting slab actually gets really shallow, and it has kind of an upward bend in it as well. And so we think that's what's actually driving this bending around the Olympic Peninsula, around the Olympic Mountains. And that bending on the north side, that's what's predicting this right lateral combination of right lateral and some compression on the northern limb. But yeah, we expect the megathrust is dominating what's happening throughout the forearc. Clearly there's still deformation happening quite far north. That Beaufort Range fault is quite a bit further up the island, and that's dominantly right lateral strike slip.
Thank you. Let's thank Lucinda one more time, please. Thanks, everybody. Have a good summer. See you in the fall. Goodbye.
I don't think they take reservations, but I'll just see that for.
You can crawl into bed if you want.
No, I want it.
Okay. Good Lord, I got snagged on you. Great job.
Thank you.
Beautifully done. Yeah. I'm sure you'll have a few folks come up here and visit with you. And then has Walter been pointed out to you yet? I'm sorry, Logan.
I think he's going to come for lunch with
Yeah.
me and Walter.
Okay,
Yeah.
great. The guy in the white hat.
Yes,
and-
yeah, we had a
Okay,
chat.
good. Okay. Okay. Well, you guys are going to lunch. It sounds like.
Yeah.
So then, when you come back from lunch, maybe we'll get a chance to visit.
For sure.
Does that sound like
Sounds
sound
good.
right?
Yeah.
Okay. Great. All right.
So I'll be around certain if I need possible. Around the building. Yeah, I should be. I don't even know if I'm going to do that research. Because I'm pushing off some of my research. Yeah. I plan to finish.
Okay, everybody. If you're still here, just a few final touches on this whole thing. Thank you for being with us live. Looks like we were hovering in the neighborhood of 350 live viewers. And I'm sure that many of you will be watching the replay of this session on Tsunami north of the border, but also down here in Puget Lowland. And I don't know, I think if you are still with us and you want to suggest some changes to this format, like if you like whatever, feedback on this whole experience as a viewer from home, whether it's live or in replay. Hannah and I continue to put this series together, and we have all sorts of interest in tweaking this and that. And I think it's fair to say that most of our attention is on people in the room and the experience in the room. But we've done most of the heavy lifting on that, and it's working. But for the home viewers, I don't know. I was noticing some of you were frustrated you couldn't see the pointer, for instance, the laser pointer. You know, speakers are nervous. They typically default to the things that are most comfortable to them. So some naturally gravitate to a laser pointer without you being able to see them. Others are a little bit more in tune with using the cursor on the laptop, and some want to use a stick. Whatever, like it, you know, that's always going to be variable based on the comfort and the setup. We were mostly focusing on this new microphone, and I'll be interested to see the replay and see how that sounded. I thought the audio, I got a text from Nat during the show saying that was working. But if you suggest tweaks on audio, what's going on with the thumbs? I'm not putting my thumbs up. Somebody else putting their thumbs up? If you have any suggestions, I'd be interested in hearing what you had to say. This is best if you're here in person.
I'm from Ireland.
And once we announce the schedule for the fall and the winter and the spring of next year, there's still plenty of seats, as you can see. And so you are welcome here. I think that I am going to try some things this summer with me teaching in this room.
Well, I briefly was.
And I just want to experiment. I'm going to buy some new equipment, I think, and I'm going to experiment with this room and some live people. So there might be some sessions in this room just to keep practicing and tweaking on what we're doing with this setup. There's some things that need improvement, but there's plenty that I think is going great. So Lorraine says the audio was great today, and it was definitely improved in the room. Let me read a few of these things live. Why not? This is the last time I'm going to see you in this format until the fall. Zoom mics for audience questions. Yeah, I've been thinking about that. I might as well respond to a few of these things right now. Why not? When I give talks, and it's being recorded or whatever, even if it's not being recorded, I insist that there's not a handheld mic being passed around the room because it just slows everything down. That's just my personal thing. I need the pace to be fast, and even live question and answer, I don't want to wait even 10 seconds for some handheld mic to be handed down to somebody and then they're like going on forever. My taste is to have it be as fast-paced as possible and getting a bunch of mics in the room so that you can hear the actual person asking the question. That's my, I'm asking for feedback and I'm telling you why it's not going to happen. Anyway, that's my taste. If a bunch of you keep saying that, then that's fine.
Yeah, I'm not sure the latest on that.
I mean, it all comes back to if I'm doing this only for you, like the alphabet series. What is that? That's just me sitting by myself in my office, and it's 100% for the viewers at home. Then of course I'm going to be doing everything I can to make the viewing experience at home the best. But this is different, right? I don't know what the percentage is. 80% of the energy put into this is designed for the people in the room, eating the Vindman's treats, drinking the coffee, drinking the bubbly water, visiting with each other. And no offense, but like 20% of it is you kind of being a fly on the wall, kind of being part of the scene, but you know, obviously I'm not asking all your questions of the speaker. So I'm continuing to think about, like, is it even worth live streaming these talks? Why don't I just record the talks? I don't know. That's a fair question, I guess. It's a significant hassle to live stream these, but there's enough of you that I think know each other, and maybe you enjoy being with each other in the live chat. I don't know. That's worth thinking about. I hadn't thought that until right now. Maybe these should just be recorded and put it on later. I don't know, let me read. I'm just feeling like I want to just spend a little time with you. It's been so long since I've been live. Lorraine loves the format. It works great. The pointer problem is an issue. Okay, yep, I can work on that. Nat and I will work on that this summer. Audio was great. For the in-room people, there was an issue with microphone technique, I suspect.
Yeah, we did lots of that when we're trying to make sense of it.
It's a long flight from Norway. Yeah, I get you.
This doesn't really happen on TBC
Not a, okay.
Oh well, I had a degree in that.
Bob Barker style long mic. Yeah, I'm very happy with that mic, but Nat strongly suggested a long cord going into the speaker. Nat says, you don't want to go Britney Spears, you don't want a bunch of wireless, you're going to need a whole mixing board to deal with all that. And I listened to Nat. He is a guiding light, for sure. Yeah, mail order Vindmans, okay. Another one, ship the Vindmans. Jeff insists that he doesn't want to do the shipping. I don't know why. Dan likes the live stream. Ivana's here. Hey, Ivana. Value for this community is all getting together. Good point. Stay live, live. It's nice to watch live. Good, okay, that's enough. Belly and up to the bar with friends. Yeah, many of you have a connection. Ivana also says, I think your audience also likes to feel connected. Good. Okay, we'll keep doing the live thing. Yeah, final comment. I'm burnt out, and I don't know why. I should be all ramped up for all sorts of new programs and things, but I just, in addition to going out occasionally with Jordan Carey or with Randy Lewis or with Gary Paul, I don't know what's going on, but I'm just, I guess I just need to take a break. I've already been taking a break. I haven't been doing much with this channel. So I don't know. I think I'm heading in the direction of a whole new set of ideas and topics, and once I get myself mentally there, I think I'll be full of new juice to do a bunch of new programs. But right now I'm just kind of in this holding pattern, and I guess it's tied to the end of the school year. I don't really know, but I don't even know what I'm saying, so I guess I'll say goodbye. Thank you, everybody. That's the end of a school year, and Hannah Shamlou and I say thank you for joining us, not only today, but all of these Friday live stream sessions. Thank you, I love you, and goodbye from Ellensburg, Washington, USA. The chatter behind me stopped because they're watching all these things happen on the screen. All right, goodbye, I love you.
Friday afternoon talk, lots of squiggly lines.